Welcome back, everyone. This is Professor Herring. In this video, we're going to continue learning about thermochemistry, and specifically Hess's Law. Hess's Law we're going to use to determine reaction enthalpies when we have multiple steps in a given chemical reaction. Let's begin. So, if we have a chemical reaction that has multiple steps in it, then it can be broken down into what are called intermediate steps. And Hess's law is a way to determine the enthalpies of reaction when we can't measure the enthalpies of reaction directly. And so this is the case for certain types of reactions that are just very difficult to make occur in the laboratory setting. So let's say that we have a reaction that goes from A to B, and there's an enthalpy associated with it. And then from B to C. Hess's law says that we can combine these two reactions, and so we would get A plus B, and that yields B plus C. And the enthalpy of that reaction would be the sum of the other two enthalpies. Because B is the same on both sides, it gets canceled out of the reaction, and so our net reaction is just A yields C. We could describe this graphically by showing the following reaction diagram, where reactant A forms B by giving off certain enthalpy, and then B forms C by giving off another enthalpy. And the net change is the sum of those two enthalpies. We call this a thermodynamic cycle. And we can apply this because enthalpy is a state function. Remember when we talked about state functions, one of the examples we gave is that if you're climbing up a mountain, the path you take is going to determine your distance traveled. However, we see that elevation is not path dependent. So elevation is a state function, whereas distance is not. And so enthalpy, because it's a state function, it doesn't matter if we went from A to B and then B to C, or A to C, it's going to give us the same reaction. It wouldn't even matter if we went from A to Z, to Q, to phi, to omega, to a star, anything to C. It's going to be the same net change. So, how does this look like in terms of a problem? You might be given some chemical reactions, and you're asked to find a different chemical reaction. So in this case, you're given reactions A and B with their associated enthalpies. We want to find the enthalpy of reaction for reaction labeled C. So what we need to recognize is that C is going to be a sum of reactions A and B with their associated coefficients. Therefore, the enthalpy is going to be the sum of the enthalpies of A and B with their associated coefficients. And we have two tools to manipulate the equations to make this happen. One is to reverse the equation, and we know that when we reverse these thermochemical equations, that is going to reverse the sign. And then the second tool in our toolbox is to multiply or divide by a factor. And since we've talked about in lesson number 1 of this chapter that because enthalpy is an extensive property and depends on the amount of substance you use, that if we multiply by a factor for the reaction, that the enthalpy is going to get multiplied by that same factor. So how does this look? Well, we know that we want to get this reaction where we have aluminum and iron oxide in the reactants and aluminum oxide and iron in our products. So what you want to do is identify for each reaction what manipulation you need to do in order to get the desired reaction. So if we just start with this first reactant in the desired reaction, we know we need 2 aluminums. Since aluminum only shows up in one reaction, that makes it a good choice. Notice that trying to balance it, figure out what to do based on oxygen is not going to be a good idea because it shows up in multiple locations. So what we need to do is we need to take and divide reaction A by a half. Then for reaction, and once we've done that process, once we've identified that that's the right step to do, it's done. We don't have to manipulate it again. For B, we notice that in this case, we want iron oxide on the left. So in doing these, we want to ask two questions. One of those questions is, do I have the right amount? And the second one is it on the right side? Or correct side, let's just say. So when looking at iron oxide, we notice that in B, we have twice as much as we need. So we need to cut it in half. But we also notice that it's on the wrong side of the equation. So we need to reverse the reaction. And so that would look like that. So for their enthalpies, we're going to do the same manipulations. 1/2 of the enthalpy for A and -1/2 of the enthalpy for B. At this point, what I recommend that you do is you rewrite the equations with these manipulations. So we've taken and multiplied the entire process by 1/2 for A, and we've reversed and multiplied by 1/2 for B. Then we can add these two reactions together. All of the reactants you write on the reactant side. All of the products you write on the product side. And then we cancel any terms that are like. We rewrite the equation and verify that it matches the desired reaction, which it does. At that point, now we can take and manipulate the enthalpies of reaction as well. 1/2 of the enthalpy for A minus 1/2 of the enthalpy for B gets us an enthalpy for the total reaction, which is negative 852 kilojoules. Okay? Now you try. Try this one on your own first, and then come back and I'll walk you through the solution. Welcome back. So, what did you do for this? Hopefully you recognized that what we need to do is we need to add together reactions A and B in some format to get the reaction C. And we need to manipulate reactions A and B, so that's going to be this process. And we need to manipulate A and B in order to make that to get the proper amounts. So, looking in our desired reaction, we know we want sulfur in a reactant. Well, B has sulfur as a reactant, but it doesn't have the proper amount. So we need to multiply the whole thing by 1/2. Oxygen we see shows up in a couple different spots, so let's ignore it for now. Sulfur dioxide shows up only in reaction A, but it's as a reactant. We have 2 times as much as we need, so we need to multiply by 1/2, but it's also on the wrong side of the equation, so we need to multiply by a negative as well. And to summarize, that would look like the following. We apply that same process, those same manipulations to the enthalpies. Now let's rewrite the equations with the adjustments. We've taken and we've reversed reaction A, and we've multiplied it by 1/2, and we've taken reaction B and multiplied it by 1/2. When we add these together and simplify, you'll notice that when we simplify, the SO3 is eliminated, and 1/2 of the oxygen is eliminated as well. Then we can rewrite that as sulfur plus oxygen yields sulfur dioxide. Check to make sure that that matches our desired equation. And it does. So then we take and we account, or we multiply the enthalpies appropriately and solve. That's it for this video. Thanks for watching. If you have questions, you can ask on Piazza, in office hours, or recitation. See you later.